So next speaker is Antoine Bosselut. I'm saying I have to say sorry for butchering your name probably. When I decided like to become a host, I asked Yufang do not have a French name. Let's see what happens. Antoine is at EPFL in Swiss. Before that, he was a long time in America. McGill, Stanford, Allen Center of AI, I think, and did a lot of work, common sense reasoning, also model editing. But today he will talk about democratizing of LLMs. The floor is all yours.
Perfect, thank you. I don't like hand microphones. Can everybody hear me? Yes. Cool. All right, let's do it without the microphone then. Hurts my hands when I hold them up. You have weak elbows, it's going to be a curse, so start working out today. Sorry?
It's not going to work.
What's not going to work?
It is a microphone.
Can you not hear me?
No.
Okay. All right, well, fair enough. I will use the microphone, and I will blame that gentleman for any elbow problems tomorrow. The sacrifices we make for our careers. Anyway, thank you very much for the invitation today to have me here. Thank you as well to the organizers for putting on such a great summer school. I've never been to Linz, so it's a wonderful opportunity. And thank you, of course, to everybody who is here and wants to hear about democratizing LLMs for global sovereign AI applications, or who is forced to sit through this out of respect. So regardless of which one it is, I appreciate you. So let's get started real quick about how AI is changing the world and motivate the topic of this talk, which is sovereign AI. Most of you have probably seen some sort of graph that looks like the one on the left here at some point over the last few years, which generally shows the rapid rate at which AI seems to be improving on a lot of the traditional tests that we use to benchmark them. And there's kind of two things to take from a graph like this. The first is that a lot of the traditional tests we often use now see AI systems have greater than human performance on them. And the second one is that the trend seems to be accelerating, where back in the day it might have taken a while for an AI benchmark to saturate, while now seemingly in something that came out in January of this year is saturated by July. So, there might be a lot of obvious reasons for that, but the truth is over the last few years, AI has gotten better, and it has gotten better faster. And naturally, a response to this particular set of patterns that we see is that there's an increasing amount of AI regulation that is passed. Naturally, the more these technologies end up influencing our daily lives and those of different citizens, the more regulation is necessary to actually make sure that that impact is contained and positive and generally welcomed by citizens as well. And finally, one of the things that we've seen as a result of this kind of increase in capabilities and this increase in regulation is something we hadn't really seen before with AI, which is conflict. Which is generally that we actually now often see some of the multinational corporations that develop these AI systems be in direct conflict with some nation states that pass regulations. And this can take the form of some services being banned in certain countries for a period of time, or essentially companies themselves deciding, well, we're not going to deploy there because the regulatory environment is too uncertain. And so it generally creates this bidirectional conflict between both sorts of entities. And naturally, one of the outcomes of this conflict is that there's generally been a push in many different places, many countries, in fact, many regions, to develop sovereign AI systems that can try to mitigate these conflicts and essentially be a balance between these capabilities and these increases in regulation as well. And for the purpose of this talk, I'm generally going to define sovereign AI as AI systems that are developed, deployed, and governed by trusted national institutions, minimizing reliance on foreign entities. It is a very high-level definition, and the actual implementation of such systems involves many low-level details that have to be taken into account, such as what type of infrastructure is actually available to deploy these systems, what type of data is used to train these systems, what type of evaluations are in the loop when you design these systems, and many, many more. But for now, we're just going to kind of use this simplified definition. And based off the motivations that I gave before, we can also come up with a good set of reasons for why some nation states may actually want sovereign AI. Kind of a classical one that is discussed these days is representation. A lot of the leading commercial LLM developers are typically focusing on, the financial environments in which they operate when they actually decide to design these AI systems. That may not naturally mesh with kind of the unique cultural environments where many of those systems may end up being deployed, such as the languages that are spoken there, the regional knowledge and the cultural knowledge that is associated with those regions. If ultimately these models are sort of developed with the, kind of a more profit-driven motivation, it doesn't necessarily take into account the unique cultural characteristics of the environments where it ends up being deployed. The second one is obviously regulatory compliance. Many different regions, many different nation states will have their own unique regulatory environments, depending on the types of trade-offs that they decide to take between capabilities, and the preferences of their citizens or of other entities in the country. And so, for 190 or so different countries around the world, you might end up with 190 different regulatory environments. Well, most of the time, the AI systems that are developed by these large multinational corporations aren't going to try and actually develop solutions for 190 different regulatory environments. And so you sort of have to take what you can get in many of these instances, which may not be what you want, or you have to end up designing regulations around what the current models actually do. And as I mentioned, this can actually lead to unstable situations where many times model developers will choose not to actually engage in a particular environment. We have seen many different cases of this, such as the fact that Meta says it wouldn't release its multimodal llama models in the EU. So here where we are, because the regulatory environment was too unpredictable. When Google's AI chatbot Bart came out a few years ago, Canada, Russia, China were essentially all excluded from being able to use it. And even recently, the US decided to ban DeepSeek from government devices, though that might be for different reasons than the regulatory environment. But generally, one advantage of sovereign AI is that you will at least have one model developer that has the sovereign interests in mind, and as a result, provides a stable solution that can always sort of be deployed in the environment that you have. Now, I'm not going to focus on the last one so much today, but I'd like to talk a bit about the first two, and specifically what we've done in Switzerland to try to ensure those in various sovereign AI solutions that we have been imagining, conceptualizing, and ultimately implementing. And hopefully there will be some knowledge to be taken about that for the rest of you today in this summer school. So, Switzerland, like almost every sovereign environment, is unique in its own ways. That's one of the beautiful things about all the different nations and regions across our planet, is that they all have their own cultural specificities. And one of the unique, I would say, cultural specificities about Switzerland is just how international it is and how diverse it is as a place, which may not be what we often think about it. But the truth is, I come from a Swiss institution, and to give you a bit of a breakdown of everything that a potential sovereign AI solution would have to handle in a Swiss environment, there are things like the fact that it has 4 official languages, actually. German, French, Italian, and Romansh are all the official languages of Switzerland. Romansh itself actually has multiple dialects, I think around 6. That have to be taken into account as well. Switzerland sits at the center of Europe, so anytime that we want to have some solution that transfers outward, it needs to essentially, be competent in the 24 official languages of the EU, as well as 250 plus potentially local languages in Europe. And also, Switzerland tends to try to stick to the EU regulatory environments naturally, because it's a pretty small environment on its own. So if we want any type of solution to grow beyond our borders, we have to address the regulatory environments that are suggested by our neighbors. And then finally, Switzerland also has, I would say, one of the largest international humanitarian communities, with over 46 international organizations being headquartered there and 750 plus NGOs, all looking for language solutions for many of the problems that they actually address, which are often not in the most high-resource languages that you might imagine. And naturally, when they come, to the universities in Switzerland and ask, "Hey, do you have a solution that we could use here?" It's not really helpful if we tell them, "Oh, yeah, but it only works in English." Does that work for you or not? Oftentimes they're asking about languages like, Hausa, Igbo, Yoruba, Twi. which are not typically handled by many NLP solutions nowadays. So as a result of this, it's quite important to actually, think about all of these characteristics when designing sovereign AI solutions for Switzerland. And it's quite complex, which, is there a problem? Okay. A feedback. Oh dear.
Come from this.
Oh, is there another microphone here?
No, it's not the problem.
Okay.
Maybe scale a little bit more in the center.
Okay.
Just a little bit.
All right. So yeah, seriously, hand mics, positions. Actually, one time I did watch somebody give a 20-minute talk without moving a single inch throughout it. I'm going to do my best to replicate it at this point in time. So you're the person I'm staring at for this. If I get off this vector, let me know. I have trouble staying still, so I'm going to do my best, but I won't. So with all that in mind, one might ask, why should Switzerland actually try to take, even try to develop any sort of sovereign AI? And I would say that there's two reasons for this, which was kind of nice and which can perhaps serve as a precursor for everyone else. The first is talent. Switzerland has very strong academic institutions, as most other countries, but it's worth mentioning as well. And the second one is that, I don't know how they thought about it, but a couple of years ago, our supercomputing center decided to buy 11,000 H200 GPUs. Props to them. I have benefited massively from this, but they were one of the first people to go after these types of graphics cards. And so, for a really nice, price, they managed to build a cluster of 11,000 H200 GPUs. Or buy the GPUs, then building the cluster was an entire other challenge. I was there for that part of it. That was not easy. But essentially, with these two ingredients, kind of, intellectual talent and, actually, the right amount of compute, you can actually start thinking about designing kind of large scale solutions that, are quite, are sort of at least, close to the magnitude of what the leading frontier AI systems are doing today. And that allows you to kind of do a different type of research when you can actually access resources of this scale and design solutions that benefit from that research as well. And one of the ways that we actually do this in the Swiss AI Sovereign Initiative is that we have these very large compute grants that are available to international folks as well. So not just Swiss folks, but also international researchers that want to partner with a Swiss PI in order to access, 500,000 or more GPU hours for a particular project that they would like to do that they think they want the scale to be able to validate at. There's also smaller compute grants as well of up to 50,000. But in general, it's about making compute available for the type of research that I think, the large scale AI of today needs in order to be understood. So I'm just going to leave this up here for 2 seconds. I saw some people taking pictures. But really, the goal of my talk today is to tell you a bit and hopefully inspire you with some of the research that we were able to do as part of the Sovereign AI Initiative, and many of the things that we learned that I think are relevant to the problems of being able to design sovereign AI. And, the first of these projects was around data compliance, and specifically trying to understand if there is a cost to actually trying to use compliant data when training large-scale LLM systems. We've heard probably from every company on earth that if they were forced to actually use compliant data and open data in training systems, their systems would be bad. Well, fair enough. Let's try to understand that though. Let's try to actually figure out what that gap would actually be. And so we try in this work that's going to be published at Column 2025, we conceptualized a data compliance gap for what would be the cost of actually training on compliant data. In the second part of the talk, I'll tell you about another myth that I've heard in the world, which is that, training on a lot of languages will hurt performance in English and overall the model's capabilities, which again, is potentially true, but then it turns off the models for a whole large segment of the world populations that may not necessarily speak English and other high resource languages as dominant languages. So we wanted to understand, whether there actually was a representation performance trade-off in multilingual pre-training. And then the last part of the talk, I'll talk a bit on our work on designing new, what we call multi-regional evaluations. So kind of going beyond this idea that multilingual evaluation should just be looking at different languages, but also looking at the fact that those languages are spoken in specific regions, and should also, evaluations in those languages should reflect the unique kind of cultural and regional attributes of the areas where those languages are spoken. So I'll start with the first one. And I guess before I get started, just a quick question. How many folks here know a bit about how pre-training data sets are curated for training large language models? All right, 3, 4 people. Okay, great. All right, so fantastic. I love having this slide then. So talking about pre-training data curation, there are a whole host of steps that you actually have to take to go from what is essentially, trillions of words kind of sitting on the web and in other places somewhere to a corpus of 15 trillion tokens that you can then just kind of input to your model, do backpropagation with, and then update the parameters. And in general, this was a figure that was released by Pinetto et al. 2024 when they built the Fine Web corpus. There's around 8 different steps that you can break this down into. The first, when you start from the web, is called URL filtering. Where do you actually go and grab information in order to build a pre-training corpus? You don't actually start with any kind of database of text somewhere. You have to go out and crawl the web to be able to do it. So you need the URLs, pretty simple. But you might want to filter it, those URLs before you send your crawler out there, because lots of things on the web, you don't actually want to actually pull into your pre-training corpus, and you can already predict what those things would be based off the URLs where they're located. The second is text extraction, actually being able to pull it. Then language filtering, depending on how you want to pre-train your language model. You may only want to focus on on content in particular languages. So here you would run a huge language identification system across trillions of tokens and only pull the ones that are in the languages you want. And then various types of quality filters, such as Gopher filtering, C4 filters, other custom filters. You would also want to do some deduplication. So typically it's believed that the more that you train on the same content over and over again, the more the quality of your model will degrade. So you typically try to remove duplicated content from your overall crawl. And then you also try to run some filters to remove personally identifiable information. So this is just regular expressions that look for things like email or social insurance numbers or names, so that they don't end up being in there as well. So there's lots of different filters that you have to do. But the important thing to remember is that when it comes to actual data compliance and trying to respect things like author rights and what their preferences around whether their data is used for pre-training, it really happens in this first step when you filter the URLs. And this is done based on typically some sort of setting that is set in a robots.txt file. But what a robots.txt file is that it's associated with pretty much any domain on the internet, and it just identifies whether you are allowed to crawl their resource for some setting for some application that you're doing. So for example, web crawlers for Google search essentially will go across all these URLs, and in the robots.txt file, there's an entry that essentially says to Google, yeah, go ahead, take our information, index it, use it as a thing for the search indexes, or go to hell. And essentially, that's essentially what is in these robots.txt files. So when you have, let's say, a public crawler, such as Common Crawl, which essentially does snapshots of the web every month or so, what they're doing is that they're just going through, and if robots.txt file says Common Crawl, go for it, they take it, they include it in the snapshot, and then if it says don't go for it, well, they leave it out of the snapshot at that point in time. Now, this becomes an interesting question to ask because over the course of the growth of AI systems over the last few years, there have been quite a few legal challenges around being able to use copyrighted content and author-owned content in training AI systems, with many different organizations actually suing some of the leading model providers for this purpose. And typically, once these legal challenges start, or even before, what many of these content owners will do then is that they will go back to their robots.txt file and they will start restricting access to their resources for many of these different crawlers. Whether it is the Google crawler or the Common Crawl crawler or various AI crawlers. OpenAI has its own, Anthropic has its own, Mistral has its own. Essentially, all these companies now have their own crawlers that traverse the web. And most content owners that no longer want their data to be in these services will now block these crawlers from actually being able to access it. And so this creates a sort of challenge, because over time, as more publishers start opting out of having their data crawled, it actually creates this gap in pre-training corpora between many of the resources, some of which we might view as kind of high quality. Typically, I assume somebody will opt out of having their data crawled if they actually think there's inherent value to their data. and what is actually left afterwards. And so what we wanted to answer is, okay, well, as this continues to go, is there going to be a downstream impact when resources are opted out of on what's on the quality of the pre-training corpora and the quantity and overall the model that you get at the end of it. And so this is the subject of our work, which is going to be published at the new or the second iteration of the Conference on Language Modeling in 2025. Can performed LLMs be ethical? Quantifying the impact of web crawling opt-outs. And what we did in this work is that we essentially took a large pre-training corpora of around 4.9 trillion tokens that was made from historical snapshots of Common Crawl. So around 100 of these snapshots that are taken month over month. And what we did is that we looked at what the robots.txt setting was in January 2025. Now, as I mentioned, over the course of the previous few years, many of these content providers have changed their robots.txt setting because they no longer want their data to be used. However, in the historical snapshots of Common Crawl, that data is still there because at the time that it was actually crawled, they had not, changed the setting at that point. But now they don't want it there. And so this brings up kind of a bit of a question, which is, okay, should their data stay in these historical snapshots as well if they now no longer want this data to be involved in AI training? So for stronger data compliance, what we did is that we took these 4.9 trillion tokens and we went back through all of the Common Crawl snapshots from which this data was taken. And we removed any URL that as of January 2025 no longer allowed for crawling of their resources by any sort of AI crawl. And that actually ends up removing around 8% of the tokens that we had in the data set. We went from 4.9 trillion tokens to 4.5 trillion tokens in this compliance data set. So it's a pretty large reduction, perhaps smaller than we might think because the web is quite big and quite large, but it's actually a pretty large reduction when we actually do this. And then what we did, if you're looking at what might actually be removed when you go ahead and do this, well, it's actually things that potentially indicate kind of high quality data. Things like stack exchange. Good luck getting your LLM to understand how to code if you do not actually have any stack exchange data in there. It's things like encyclopedias. So things like, there was an encyclopedia here somewhere. Four. Yes, Wikia. That's not encyclopedias actually, but close enough. Is now no longer there. Just things like WebMD and Biomed Central, which might have various types of health data, Medical Express, Scientific American, and of course, some of the biggest sources of news and truth that we might have, such as the BBC and New York Times. All these things are essentially gone once you start removing this. So it's potentially high quality data that is leaving here. But so what we wanted to understand is, okay, we're potentially getting rid of a lot of this high quality data. What actually happens downstream to a model where this happens? And what we learned, I guess, as we did this, is that it's actually a very complicated question. But I guess let me tell you how we approach this. The first is that we set up a new measure that we call the data compliance gap, which is essentially what would happen if we trained the model in two settings. One only on the compliant data and one on the non-compliant data, and then trying to measure their performance across various benchmarks at the end, average that performance, and essentially decide this is what the data compliance gap across these benchmarks is if we actually remove this non-compliant data from the training corpus. The second setting we did is one that looked at what's called continual pre-training or mid-training nowadays, which is, you start off potentially both training on a compliant corpus, but then afterwards at a different stage of your training, you might add new data that would be non-compliant. And the reason for this is that we may come to settings in the future where you might do a large amount of pre-training solely on compliant data, but then afterwards might be willing to pay content providers to actually train on their high quality data. And if you do it this way, you would probably want to do it in such a way that you're only training on this non-compliant data at the end, because that is generally where you'll see the most impact from that data when you do the training. So we measured this data compliance gap in both the mid-training setting and the full pre-training setting. And what we actually generally found is that there's not actually much of a data compliance gap in general knowledge understanding when we actually train only on compliant data. So here we did pre-training with around 1.5 billion parameter models and around 100 billion tokens that we trained each of those models on. And then we evaluated it on benchmarks generally linked to kind of general knowledge like ARC Challenge, Common Sense QA, Open Book QA, Physical IQA, Winter Grande. And generally what we see is that apart from, a few settings, there's not really a huge gap between these two cases. So, overall, it seems to indicate that there's not much of a data compliance gap to actually forcing people to train on compliant data. A couple caveats, the main obvious one is that this was only trained on 100 billion tokens because it costs a lot to train on 4.5 trillion of them. So it's possible that as you keep scaling this up and looking at more data, that data compliance gap might grow bigger. It's also only 1.5 billion parameter models, but we also played around with 3 billion parameter models and didn't see it there as well. However, in the second setting, we did start to see slightly bigger differences where once the model has kind of been trained on enough data, if we start reintroducing non-compliant data from very high quality data sources, now all of a sudden we do start noticing a data compliance gap, for example, in medical domain data. So being able to train on medical encyclopedias in this mid-training stage did lead to a gap compared to not actually training on this data at all. And this was kind of especially noticeable once we increased the amount of tokens that we trained on to 1.7 trillion tokens with these models, we start to see kind of a larger gap emerge between the compliant data and the medical data as opposed to just the compliant data in the first place, around 2% or so when we do that. So at a certain point, when you train enough tokens, there are some indications that in very kind of specialized domains, there does kind of seem to be a data compliance gap that emerges. This was not the case, for example, for just adding back news data or math and science data. It was really for kind of the specific medical domain on these medical benchmarks that we started seeing this data compliance gap emerge. So the takeaways from this essentially was that we identified a data compliance gap to try to measure what would be the cost of data compliance when training LLMs. And we generally didn't see that big of a gap when retroactively applying publisher web crawling opt-outs on pre-training data. However, for specific domains, once we actually started adding back that content during mid-training, we did start to see a slightly larger data compliance gap emerge. One thing I do want to mention here, though, is a potential pitfall here that we learned about later on, which is just removing domains from your data set doesn't necessarily remove its content. So there's a phenomenon online called content republishing, which is essentially that a whole lot of people will just take content from, let's say, produced by the New York Times, copy it word for word in a blog, and put it out there. And so even if you actually if you look at, let's say, the New York Times data and you try to remove all links to the New York Times, you will remove only about a third of the mentions of the New York Times articles that you have in your data set. And unfortunately, you can't really track down every single mention that you have using these types of exact match filters. So one thing to take this with a grain of salt is, this is measuring a data compliance gap where we explicitly remove the links where that content is published for, let's say, the first time, but it may not necessarily remove all of the content, all of the mentions of that content online, because it may have been republished elsewhere by entities that don't actually opt out of this AI training. So one thing, a sort of thing to keep in mind as we look through these results. The second thing that we wanted to look at as we started training sovereign AI systems was how do we actually make sure that the languages that are important to the context of Switzerland are actually well represented in multilingual pre-training data. Just to give you a reminder, Switzerland is quite a multinational place, both in terms of its country itself, multilingual place, both in terms of itself, where it is in the context of Europe, and where it is in the context of the world. And so our goal was to be able to say that we could train the model on hundreds, if not thousands, of languages. But first, before doing that, we needed to study what the impact of including this many languages in pre-training would be. And when we do this, so we wanted to essentially train a model that intentionally represents as many languages as possible. And when we do this, we kind of find that there's two challenges for this. The first is, how can we reliably identify many languages in web data? And the second one is, how can we make sure that their inclusion doesn't negatively affect the performance of the model in other languages? Now, if you've been in NLP a while, you'll kind of know that the first one here is a task that's pretty common that is called language identification, where you essentially, given a piece of text, try to identify the language that text is actually written in. And pretty much, that language identification step happens here in the language filtering stage. Now, a couple of years back, when people were first kind of creating large-scale pre-training corpora, the goal was, I would say that NLP was a lot more focused on English as a language. It is still, to an extent, far too focused on English, even as we're in the LLM era. But back then, essentially, when they created pre-training corpora for a lot of these initial models, in this language filtering step, what they did is that whenever the language ID system identified a language as non-English, they would throw it away and only keep the English data. So lovely models then would be left afterwards for using it. Nowadays, typically what happens in these steps is that you might pick, let's say, 20 high resource languages that you want to pre-train your model on, select those, and anything that is not in those 20 high resource languages gets thrown out, which is also not ideal for any language that's outside of the top 20. And then finally, a third challenge that often comes up in language filtering is, what does your language ID system actually look like? So for many years, the top performing language ID system actually only handled around, anybody want to take a guess how many languages? All right, let's say A, 37, B, 123, C, 176, or D, 232. Who thinks it's A? I just made all those numbers up, by the way, but only one of them is true. Who thinks it's B? Who thinks it's C? And who thinks it's D? It's C. It's 176. Now, why is that number important across those four random numbers? It is because when that language system was first conceived, that was the number of languages that were in Wikipedia. So when they trained the language ID system, they went for the amount of languages that were in Wikipedia. They created a great LID system for those 176 languages. And if you spoke a language that wasn't in those 176, tough luck. So this is kind of an interesting, case study on, how the digital sphere actually drives a lot of the decisions that are taken in time, and how decisions from a particularly point past in the day actually get maintained, for perhaps decades at a time, simply because everybody's like, yeah, 176 languages, great. That's way more than English. So let's just stick with that. And it was actually only, I think, around a year or two ago that somebody first actually decided to say, well, maybe we should expand that quite a bit. And really, that was this work by Glot LID from Hinrich Spitzer's group at LMU Munich. Fantastic work that essentially said, why don't we actually try to expand language ID to around 2,000 or so languages? And it was a great work. And one of the big challenges when you actually want to scale LID up to thousands of languages, particularly for pre-training corpora construction, is that you really need scalable and efficient methods to actually be able to do it. And the reason for this is quite simple, is that if you have to run a language ID system on billions of documents and trillions of tokens, it better be fast, or you're going to be waiting for years until you have your corpus back. So this isn't really something that you can kind of run kind of a 7B or 8B language model or 1B language model on. For a long time, this was pretty much try to predict it from just word embeddings, because that's the only way that you can actually scale up that solution. The second kind of two challenges is that when it comes time to actually reliably identify low resource languages, you have a few issues. The first is kind of this big class imbalance problem where you don't have a lot of supervised resources for actually identifying many low resource languages. A lot of those resources end up being mislabeled. And the second thing is that you tend to only have data from a few very domain specific corpora. So the thing is, like, once you get outside around, I think, the top 400 languages in the world, there's kind of only two sources in which you're actually going to find data in low resource languages. The first is religious texts, where essentially the Bible has been translated to around 1,400 different languages, so you're good to go on those ones. And the second one is advertising, which is also not the most high quality data to actually try to construct a language ID system from. So you kind of have to be able to deal with these different issues when you actually want to design LID systems that can be reliable in many of these languages. And this is essentially what we tried to work on in a recently pre-printed paper that we called CONLID, Contrastive Learning for Low Resource Language ID. And the idea behind this work was, how can we actually use contrastive learning related to the language that is identified in a text and, what we call the domain or kind of subject of that text, like advertising, like the Bible, in order to try to disentangle them and get more reliable language ID systems. I won't bore you kind of with the method itself, though you should check it out. But, I think the important point here is that we did get a kind of fairly substantial improvement on low resource language performance when we actually ran our LID system in this way. And we also got fairly large improvements for less common scripts. And this was with a minimal degradation for other high resource scripts. So you can still work on these problems that are often considered solved, like LID, once you kind of start recognizing the challenges of them in the first place, and then make kind of significant efforts to improve this. The second challenge, as I mentioned, is obviously we want to be able to have very large scale representative coverage of many languages to kind of increase access to these tools for many communities. However, at the same time, there's been these these questions over the last few years of whether that can hurt the performance on your other more high resource languages to actually try to represent these other contexts in your pre-training. So this is work that we took a look at in it's not on archive yet, though it should be soon. A paper called Debunking Data Myths for Training Large Multilingual Language Models. And in this work, we specifically tried to address some of the kind of prevailing wisdoms that have emerged around training multilingual systems. And a big one, is this often cited curse of multilinguality, which essentially says that, as you add more languages into a model's pre-training corpus, you will generally lower the performance across all of the languages. And so what we wanted to ask is, okay, well, let's take a look at what the assumptions are behind that curse of multilinguality, a big one of which is you have a fixed capacity of pre-training data for these languages. So you have 100 billion tokens and you just start adding other languages, sometimes uniformly in terms of size to that mix, which means you're necessarily lowering the amount of data that is in your overall mixture. However, this isn't necessarily the way constructing pre-training corpora actually works. If I have 10 billion English tokens and I want to add 1 billion French tokens to that, I don't need to remove 1 billion English tokens necessarily if I have the compute budget for it. In a case where we have more limited compute, then you need to be more creative. But in our case, we wanted to just see, okay, well, what happens if I just grow the size of these corpora as opposed to trying to kind of balance them within a fixed budget? And what we generally found here was that you actually don't necessarily have this issue. Obviously, the more English data you have in a fixed token budget, which is here on the right in this maroon setting, you end up hurting multilingual performance. As you see kind of English grow up as a proportion of your overall corpus, you also see that the loss on multilingual, on other languages goes up during this point in time. And that's precisely what you don't want. However, at the same time, what we saw is that when we just increased the amount of English in what we call a fixed multilingual budget, so we have all our multilingual data in the corpus, then we grow English as far as we want. What we saw is that it actually stays pretty consistent and doesn't really have a negative effect on multilingual performance while the English performance keeps improving. And so as a result, what we kind of said from these ratios, okay, well, let's just kind of stick at that 60% magic number of English data, because at that point, we probably will not have a huge drop in multilingual performance if we keep all the multilingual data that we have that is of sufficient quality. And the nice thing about this is I showed these loss curves, but it tended to work when we started looking at the benchmarks as well as we did this training. So based off that formula, we started training kind of 8 billion parameter models on, well, I guess the overall targets here was around 5 trillion tokens of text. And what we saw is that our Apparatus 3 AB model essentially kept up with Olmo 2, which was a 7 billion parameter model, as we had this language mix. Meanwhile, of course, in the multilingual settings, it was much better than pretty much everything else that was happening because we were able to train on all this multilingual data. So it was quite promising that we weren't necessarily suffering on some of these benchmarks in English, even while we maintained multilingual performance. We saw some challenges later on that I'm happy to discuss in the Q&A. But if overall, in terms of this multilingual performance, it seemed to work pretty well. And it gave us, and so the takeaways here were that essentially, when we wanted to be able to create kind of more representative multilingual pre-training data, we had to expand, language representation while taming the curse of multilinguality. And the way that we approached this was, one, by getting better language ID systems that can learn from script and domain-aware negative example mining. And the second one was, have a sufficiently large budget of multilingual data, and then you can keep increasing English to capacity without necessarily affecting performance. So it's these fixed token budgets that are a problem. So really the curse of multilinguality, I would say, is more a curse of capacity. It's not necessarily something special about just having more languages. It's can you get enough data in all of your languages under a kind of a fixed budget so that you don't have this problem. Well, another way of fixing that problem is just increase the budget so that you can increase everything that you want at that point and make the models big enough as well. And kind of taken together, this kind of sort of gave us enough confidence to really scale it up. And actually, we've had a 70 billion parameter model that has been training for around 2 months now. And that is being trained on around 15 trillion tokens of text. And actually, I got a message at 2 a.m. this morning that it was done training. So it should be released roughly the next month. Thousands of languages in the pre-training corpus, data compliance according to the recipe that I just described to you, and all checkpoints will be released for transparency as well if you'd like to work with these types of models for what you do as well. So obviously we're doing some simplified post-training steps over the next month to get it to a higher quality level even more, but it'll be available as a research artifact at the beginning of September. And if this inspires you, we're actually hiring engineers. We're always looking for research collaborators. So get in touch. How much time do I have? I don't actually know. 10 minutes? All right, well, let's wrap up quickly.
13 minutes.
I have 30 minutes left? Oh, 13, okay, all right. Sure. It's like, it's gonna be a long QA. It's gonna be a long Q&A session. Hope you guys are ready. All right. Thank you, that's my mistake. It's the elbow, it's messing with my mind as well. So the last part I want to talk about is actually what is one of my favorite topics. As we launch this project, or how can we actually create kind of large-scale multilingual systems, one of the challenges that we ran into is we weren't really inspired by many of the kind of standard options that folks were using in LLM work for multilingual evaluation. And so I guess to motivate this, I'm going to give you an example of this benchmark that has become pretty standard. It was released by OpenAI, so one of the leading kind of developers of LLMs. And essentially, it takes MMLU and translates it into 14 languages: Arabic, Bengali, German, Spanish, French, Hindi, Indonesian, Italian, Japanese, Korean, Brazilian Portuguese, Swahili, Yoruba, and simplified Chinese. And this is obviously kind of great to expand into multilingual capabilities. To pick languages that cover large portions of the world. But there's a few issues with this. One, it's only 14 languages that are now covered as part of this data set. And the other one is a bit kind of more subtle, but quite there. And it's also in pretty much every benchmark that was created for this purpose. So then, there were follow-ups. There was this open multilingual LLM evaluation leaderboard that now, expanded these benchmarks. They translated ARC, they translated HelloSwag, they translated Truthful QA. There was an open European LLM leaderboard that took MMLU, the same data sets, and translated them across, all of the languages of the world, and of Europe, my mistake, the main ones, primary official ones. And essentially, this is how multilingual evaluation was going. And there's a bit of a problem with this, which is that languages and typically the users that speak them and the queries that are posed in them are actually kind of reflecting regional and cultural specificities of the environments where those languages are spoken. What does this kind of mean in practice? Well, it means that somebody that is asking about an LLM a legal question in, let's say, Swahili, which is spoken as an official language in Kenya and Tanzania, is probably looking for an answer that is grounded in the model's understanding of Kenyan and Tanzanian law, and would prefer to have that language model be evaluated on such a benchmark, and not whether this model understands US law in Swahili, which is perhaps less useful to that user. And this is a challenge because the benchmarks that are being translated have this very strong US bias to them. So in a recent work that's actually going to be presented next week at ACL 2025, that was done with collaborators at Cohere for AI, we essentially annotated the entirety of MMLU with different tags for, is there a regional bias or a cultural bias to this question? And what we found is that, there were many questions, obviously, that were culture agnostic. Math is kind of the same. Wherever you are. But there were quite a few questions that were what we call culturally sensitive. And in those, when we started looking at what the model looked at, when we started looking at what was the bias of that culturally sensitive question, we found that actually most of those questions, around 65% of them, were regional to a North American context, 20% to a European one, and that overall, culturally, there was around 87% bias towards the Western Hemisphere. And that's a bit problematic because that means that most of these evaluations are perhaps, whenever there is a bias to reflect, are reflecting one of a particular part of the world. And so instead, what we decided to do is, actually create multilingual evaluation benchmarks that focused on regional knowledge. So this is work that was published at ICLR 2025. It's a work called Include. And what we essentially did in this work is, perhaps a bit uninspiring from a methodological perspective, but I think quite useful from a practical and impact-wise, is that we worked with native speakers of many different regions to actually collect around 200,000 MMLU-style MCQA questions from academic exams, from professional certification exams, from occupational license examinations. And we ended up with a benchmark that covered around 44 languages from around 44 language regions as well, 750 exam sources, 15 scripts, and overall representing a much more diverse array of regions than we would typically see in a benchmark such as MMLU. And we released multiple versions of this benchmark with around 25,000 questions and 12,000 questions, where we actually sample based off the number, where we try to sample a uniform number of questions for each of these languages in each of these regions, so that it's actually kind of a broad evaluation of many cultural environments. And what we find here when we ran quite a few prompting strategies, things like using the same prompt in language, using an English prompt, using an English prompt with a regional instruction, or an in-language prompt with a regional instruction, what we find here is that these numbers tend to overall be a lot lower than what you would typically see in an MMLU style model. So you're often losing kind of 20% or so in most of these open models compared to MMLU performance. And then of course, we kind of find things that you would expect to be standard. GPT-4o was the best model when we ran this compared to many of the others. In general, the bigger the model, the better it does on these regional examinations. It's not too surprising. And finally, one thing that was a bit surprising is that some of these models actually work better with English prompts, even if then the question is in the regional language, as opposed to having both the prompt and the question be in the same language. So some models such as Aya or Quen would benefit from the English prompt, particularly at a higher scale, especially in a zero-shot setting, while others actually like Llama prefer the in-language prompt. So there's kind of a bit of diversity in how these models respond to different settings, and you have to be careful of all these when you're running a multilingual evaluation. What was interesting as well, and this I would not say is a particularly robust result, because a lot of these exams come from different sources. But one of the things that we noticed as well is that when we took in each language an exam corresponding to, let's say, regional history, so in Armenia, it would be like a history of Armenia exam, and then also a global history exam, so like world history in that context. Almost all these models tended to score better on the world history exam, which we, once again, is a little bit of evidence that generally these models have a better understanding of kind of the global perspective, probably driven by Western norms, as opposed to the regional knowledge that's associated with these environments. So, a justification for us for why it was a good idea to actually create this regional benchmark in the first place. So the takeaway here is essentially, use Include if you want kind of multi-regional evaluation, as opposed to only using translated benchmarks in your evaluations. And naturally, what we've been really excited about as we saw this is that it's actually made its way into the development pipelines of some of the kind of leading frontier model creators. Cohere, that one's kind of a cheat code because we worked with them on it. But also the Quen team is now also evaluating using Include, which we view as quite inspiring as well. And naturally, our next steps here is more languages and more regions. In the first version, we had around 44 languages in this resource. Right now, we're getting ready to release V2 in the next few months. We're at 120, what I would call language regions. So naturally, many languages are spoken in different regions as well, and you want to be able to represent the unique regional environment. I'll use French as an example. It's spoken in France. It's also spoken in Switzerland. is spoken in Canada, the type of knowledge that might be associated with each of those regions in that language is quite different. The same is true of Arabic, the same is true of Spanish. It's important that actually the various diverse regions where those languages are spoken is used, and that it's essentially not only showing one perspective from one country in each of those languages. So now we're at around 120 language regions across 89 languages, and we'd like to grow it even more. So if you're from a region that you think should be represented, please feel free to reach out. We'd love to make sure that it's represented and include V2 in the future. And so that's it. This is what kind of goes into actually constructing data and evaluations when you want to pre-train kind of large multilingual AI models, either for sovereign or non-sovereign purposes. How do you actually try to model the regulatory compliance of the environment you're in? How do you actually measure that representation performance trade-off in terms of how many languages you represent in the model? And then finally, how do you make sure that you have the right North Star? And as you make all these decisions, you're actually driving towards an evaluation metric that is actually a reliable measurement of the goal that you have. So yeah, I guess I just went through all that, so I won't repeat it, but look for the release of our models that have been built using these principles in September. And if these types of topics interest you, feel free to reach out and let's work together on open democratic LLMs. Naturally, perhaps most importantly, I just get to highlight all the work that these folks did, but really the true workers are my collaborators from EPFL, from Cohere for AI, from ETH Zurich, Sony, Meta, Swiss AI, and more broadly. They're the ones that actually do the work, and I just get to then highlight, all the great things that they've done. So thanks so much, and I don't know how many of us did 2 minutes.